Okay, so let's start with an outline. We'll talk a little bit about FHE going mainstream and what, in our view, some of the key requirements are. And then I'm going to finish my bit by giving a little look ahead into the future, because one of the things I really want to stress is that Optalysys is actually a photonics company. So one of the things that makes us unique and different is that our genesis, our origin, our background is in photonic technology, and we'll give you a little bit of a preview as to what that means in this space. Okay, so that's the outline. So let me introduce the company, where we fit in the secure computing environment, and I'm going to do it from several perspectives. So start with the basics. We're a UK company, as you can probably guess. Headquarters in Leeds in the north of England. And we've got two main offices. We've got the Leeds and the Bristol office in the southwest. And then some of us, like me, are remote. And we are a diverse bunch of folks with a range of backgrounds. We've got cryptographers, we've got digital and analog engineers, we've got a photonics team, we've got a product and commercial and marketing teams. So quite the mixture of people. And I think it's that combination of wide skill set that makes us somewhat unusual and hopefully interesting. So we are a 50-person company at the moment. We're funded by a bunch of investors, very supportive investors, and there'll be more in the future around that side. And yeah, Zama is a very important partner for us. So again, big thank you for letting us come and talk today. So where do we fit from a Zama perspective? So this slide is actually from the State of FHE report. So the version that was published at the end of last year. So a lot of you will have already seen this kind of roadmap with the acceleration of FHE being a really key factor, the thing that's going to unlock new use cases. And there are different hardware platforms that people can use to accelerate FHE. So today, CPUs can be used, but also GPUs, ASICs, and photonics. And I think the unique thing about us is we do the full range. So right through from CPU, GPU, FPGA, ASIC, right through to photonics. So I'm not aware of other companies that have quite that breadth of coverage. So another way of asking where do we fit in is looking at the Zama architecture. So if you look at the blocks and the different bits, it's the actual FHE coprocessor, which is where we play. That's what we accelerate with our hardware. So we'll talk more about our products a bit later, but as part of the wider system, it's the coprocessor that we're most interested in. Yet another way of looking at it is where do we sit in the stack? So if you're here from more of a software or systems background, we are at the base layer, the hardware layer, and then we've also made an API interface to the tfhERS library that Zama have, and then in turn to the fhEVM higher level software above that. So our goal as a company is to be the bottom layer, the hardware accelerator for a wide range of different platforms, different schemes, different partners, to be as agnostic as possible. And then finally, more from a product and business model perspective, the way where we see ourselves is we want to be a key partner to Zama and some of Zama's customers. We have a particular focus, I think, on the enterprise side of the market. So enterprise customers, maybe banks or stablecoin operators, rather than the consumer side. We want to help bring FHE acceleration to that. And the way that we have positioned our product, which we call LightLocker Node, is it's the world first enterprise-grade FHE accelerator. And I will talk more about it later. So we're looking to offer, with the support of Zama and other partners who we can talk about more another day, a full deployment solution. So take the Zama reference architecture help customers to adapt it to their particular use case and provide them with the key acceleration hardware. And one of the things that Joe's going to talk about later is our testnet that we have created based on the Zama reference architecture, but running our own hardware. So I won't say more about that at this stage. Okay, so now we have a little section about the product itself. What is LightLocker Node? We'll start with a little animation just to give you a visual flavor. So as you can see, it's designed for a server room, whether that is your own personal server room or a shared data center. It's a 2U high server rack, and inside it's got a chunky CPU and 3 V80 FPGAs. And between the CPU and the FPGAs, we do a big acceleration of the phE. So we first announced this product in Cannes at ECC, and we pre-announced it, and the goal is to be shipping imminently. We're just waiting for our export license at the moment, but it's basically there. We've got units, and aiming to get them in the hands of customers very soon. As I said, can be deployed anywhere. Doesn't matter whether it's public cloud, private data center. And the way we are differentiating it, as well as the performance, is the targeting of enterprise customers. Enterprise customers don't just want a bag of bits and some instructions. They want an appliance that's reliable. They want a service contract that goes with it. They want professional services to help them implement it. So that, with our partners, is what we're intending to offer. So I've got a little segue for people wondering how we do our acceleration, what's our approach, because there's a few different people in the space and everyone has a slightly different approach. I apologize slightly for the way I've described it, because I'm a simple person who likes to understand things in simple terms. So let's start with the example. So the base use case is a token transfer, a confidential token transfer from two people. So from Alice to Bob, they want to send some tokens to each other, but they want to hide the amount that's being transmitted. So that transaction is actually made up of 4 low-level phE operations, like add, subtract, less than, etc. And from a processor point of view, each operation has a different shape. So by shape, what I mean is it can be parallelized to a different degree. There's a function in TFHE called the programmable bootstrap, which is the bit that we really accelerate. So different functions have different numbers of PBSs. So if you think of it as a Tetris shape, the challenge for any hardware accelerator is how to get as many of these transactions through the pipe as quickly as possible. And because the operations have different shape, you run the risk, if you're not careful, of sort of wasting space in your pipe. So think of it as a pipe that you're trying to fill, and you're trying to minimize the white space in here. So by using a CPU to do the orchestration and then the FPGAs to do the heavy lifting, what we aim to do is a bit like doing Tetris in real time. We try and pack that pipe as optimally as possible, and that's how we aim to get our maximum throughput. And one of the things that we have observed is, obviously, benchmarks are very important. People publish benchmarks. Zama are at the forefront of publishing benchmarks in a very helpful way. But there is a difference between the benchmarks for a single transaction and for trying to send thousands through the pipe as fast as possible. So the system behaves slightly differently. You get congestion. So we believe that the most useful metric is a sort of bulk transaction metric. And that's what we've been seeking to optimize. I'll just walk you through. We've basically got a couple of graphs that show the performance of our system against a 2 GPU system. So again, we go back to what is a confidential ERC token transfer. It is these 4 steps. I said there was an add, a subtract, a comparison. And this is why that's true, because in terms of what you're actually doing, you're subtracting an amount from a sender's balance, you're adding it to a receiver's balance, you're checking that the sender has enough funds in their wallet, etc. So that is the transaction. And here we have a little animation showing in green, we have a GPU sending a whole bunch of transactions. And the gray and blue one is our system. So what you see is that for the first few transactions, we have a higher latency than the GPU. But as you continue sending lots and lots of transactions, the way we do it actually leads to higher throughputs, almost twice as fast compared to the 2 GPUs. So for a real-world use case, it is a very good way to do it, we found. So, slight change of gear. One of the things that we want to think about is if you're actually deploying this in practice, if you are a developer, if you're someone who writes smart contracts, if you're someone who wants to develop a dApp and you're concerned about performance, what tools do you want in order to help you predict performance and also to help you to know which hardware you should be running on to get your level of performance? So we've made a little tool which looks like this. So it's inspired by one of those product configurators. If you go to IKEA, you want to buy a double bed, you can choose your model, choose how many drawers it has in it, what color it is, etc. So it's a bit like that for FHE. So you start off by choosing your smart contract. So we give you 3 example contracts to start with. There's your basic token transfer, there is a blind auction, there is confidential voting, and then you can actually upload whatever smart contract you want, and our tool will parse it and will predict the performance. So step 1 is choose a smart contract, and it will show you the code from that contract. Step 2 is within that smart contract, you'll have a bunch of functions. So you can go in and say, okay, I want to choose this function and I want support. So the Zama model and the one that we've been using is the coprocessor model, where the validator nodes in your blockchain, you're not doing the FHE computation on every node, rather it's offloaded to a set of coprocessors, and you can choose basically how many coprocessors you use. So the absolute minimum case would be a single coprocessor with an optimistic calculation, or more common, you could have a little consensus ring of coprocessors who could then each calculate the results and vote on the correctness of it. So in this case, we're going to say we're going to use a consensus network with 3 coprocessors. And then finally, on the last page, it summarizes what you've chosen, what your selection is, and it says, okay, how would that translate into how many hardware units you would use? So in this case, you would need 2 of our LightLocker Node units per node, and you've asked for 3 nodes, so you would need a total of 6 servers, and that would give you 200 TPS, which is higher than your required 150. So this tool is quite useful, and although the URL may change in the future, we're going to give it a slightly more friendly URL. If you want to play around with it and have a preview, it is live now. You can go try it at that URL and run your own smart contracts through it, and we would love your feedback from it. So that's a little bit about the tools. I'm just going to step up a little bit. So we're all interested in FHE going mainstream. So what, in our view, will it take for FHE to go mainstream? And I've picked out 5 elements here. So the first one, really basic, what's the economic incentive for FHE going mainstream? Well, hopefully the fact that you're here means you don't need persuading of this. But the way I would summarize it is there's a whole raft of real-world use cases which simply don't work if you don't have privacy. So this guy, Jeremy Allaire, the CEO of Circle, we like to quote him because he came up with a nice way of summarizing it. But as he said, most businesses won't touch blockchains for a lot of business operations unless they can offer confidentiality and MEV and front running and sandwich attacks is one example of that, but pretty much any real world use case doesn't really work unless you have confidentiality. So the economic incentive is definitely there. Second thing is you need the regulatory framework to be right. And I think that the stars have kind of aligned in that sense. So we've had things that drive demand for confidentiality, like the GDPR and DORA and the CCPA. And then in the last few years, we've had more clarity on the actual deployment of blockchains and stablecoins with the MiCA Act in the EU, and then more recently the Genius Act in the US. And that has really kickstarted a lot of stablecoins, a lot of deployments. So that's another tick in the box. Third thing is a mature software platform. And Zama really are leading the way in this. So hats off to them. I think I was at the Zama event last night where they were talking about the latest rollout of things. And it's really striking how the space is maturing and various companies like Zama are taking the lead to create a stable platform. Fourth thing is the developer ecosystem. So that's you guys. So it's all the people developing the dApps and the protocols and the use cases. Very, very important. And then finally is the scalable infrastructure. So obviously that's where we come from. That's our focus. And why are we always talking about faster and faster FHE? What is the opportunity? I think the next slide shows something interesting. So if you look at top blockchains and what their maximum throughput is, you can see that in order for us to bring FHE to all the different chains, we need to go faster and faster. We need to keep pushing on the FHE acceleration. And at the bottom, I've just shown for context the speed and the throughput that the major payment chains can support. So if we want to be competing with those and allowing mainstream payments to be on the confidential blockchain, we need to be in the hundreds of thousands of transactions a second, really, to be competitive. And that's part of what drives us in our roadmap. So the TCO, the total cost of ownership, is very important as part of how we communicate our value prop. And if you are an enterprise investing in any kind of hardware, you need to have some confidence that when you buy equipment from a company, it's not going to go obsolete really soon. So we have deliberately designed our products to be scalable and expandable and to be a future-proof investment. And that is a nice segue into the future for Optalysys. So I said at the start that we are actually a photonics company. And I'm just going to finish my little slot by giving you a look ahead, a peek to our photonic future. So although our product today is FPGA-based, what we really see as the future of FHE is something a little bit like this, where you have a mixture of digital silicon cores doing different processing, but you also have a photonic layer where not only the transport, the data flow between different blocks, but even some of the processing itself, the really heavy lifting, can be done faster and more efficiently with photonics. So that's what we are working towards. And I just wanted to show you that it's not all made up. There is some proof we can show you. So this is a picture of a silicon photonics device that we've created. It's actually a 4-channel optical Fourier transform. You might think 4 channels, that's not very big, but actually the way these can be used combined, you can make arbitrarily big transforms. This is what it looks like in practice. So it looks like a fan or a section of a cogwheel, and you have 4 optical channels coming in, and the light naturally diffracts, and by reading the outputs at the different teeth of the cog, you can, for free, get the optical Fourier transform of the inputs. And in fact, you can do more than that. You can do all sorts of clever things. So this is what it looks like schematically. So it's a 4-channel optical compute element. So you can actually configure it to do different things. And in the next slide, you show how this can be used to do an NTT. So an NTT is like a fast Fourier transform, slightly tweaked, and that's the dominant format of processing for not just FHE, but a whole class of related cryptographic problems. And I'm just going to leave you with this diagram, which just hints at the bigger picture. So the things I've circled in red is what we've been talking about today. So we've been talking about FHE, we've been talking about TFHE as the particular scheme that we're using here. But the point I want to make is there is a common factor linking all of these different areas, which is the type of math or maths that it uses, which is this polynomial modular arithmetic maths. And in principle, if you make hardware that can address TFHE, it can in the future do a much bigger range of applications. But I'm not going to say more about that today. So Whistle Stop Tour, thank you for paying attention. I'll give you a minute or two to sip your coffee and take a breath, and I'm going to hand over to Joe, and Joe's going to talk about our testnet and also introduce the interactive part of today's session. Thank you.
So, first of all, hands up, show of hands. Who caught Vitalik's comments yesterday at the introductory session? Like where he was talking about how you need to build on Ethereum, how you need to be able to work with Ethereum. I don't know where what we've done kind of fits in with that, but I think we are definitely building one of the many rungs on the ladder of Ethereum. So today I'm going to demonstrate our testnet. So we've built this out of a combination of our own LightLocker technology, but also the technology of Zama. So first things first, we kind of need to understand the Zama architecture in context, and that will help to understand our own testnet architecture in context. So what I'm going to briefly do is, to help explain this, I'm going to put on my own Zama hat that I've had for some time now, because like we started working more formally with Zama back in 2024, but they've actually been like a guiding light in this space for us ever since we realized that what we were doing in optics could actually be combined with FHE to create like a very, very fast, efficient processor. So how we understand Zama's approach to this and how you bring FHE into the blockchain is, first of all, you've got like the gateway chain, which is where we offload all of the super intensive compute, all of the key management stuff, all of the stuff that's very specific and bespoke to FHE and making that work. So that includes obviously the FHE co-processors. It also includes things like the key management systems as well. So like the secret sharding approach to key management, which is kind of how you make all of these different ciphertexts, all of these different users, how you make them compatible in terms of compute operations, how you ensure that people can encrypt and decrypt in safety. Then you've got like an L2 type chain, which is actually running the fhEVM runtime environment. And then you have like the rest of the network. So you might have like an L1 base chain where you're sticking your Merkle proofs and what have you. Obviously, like it very much depends on what you're trying to accomplish. And this is kind of how we see like a basic transaction on this network working. So if you're from Zama and like take offense at this and our attempt at explaining your own gateway chain to you, please put your hand up, collar me at the end of this and maybe correct what I'm saying. But let's say we want to transfer 2 tokens between 2 different users. We have user 1 who would deposit their tokens in an L2 bridge contract that would be picked up by an off-chain watcher, and you would mint your tokens on the L2, and that would store a ciphertext in the gateway chain containing the tokens that you've locked up on that L1. And then you might interact with like a CERC20 contract, and that would initiate, as Nic says, a sequence of compute events to be emitted from the fhEVM runtime. These get picked up by the FHE co-processors, and because there's no specific ordering to them, it's not like you're passing out a batch of operations at once, they're kind of being emitted at the pace of that L2, then you'll have a mix of different operations corresponding to different transactions being emitted there, and that's what we kind of pick up, and that's what we leverage to kind of make the FPGA-based systems considerably faster. So the FHE processors have their own consensus sort of mechanism for making sure that they all agree on the outputs. The results are then sent for consensus, and the ciphertext gets stored after the compute operation has happened. And then if user 2 wants to inspect their balance, they can request a user decryption. Now, there's a bunch of different ways of decrypting under the KMS that Zama has. You can have a public decryption, which is where it's exposed to everybody, or you can key switch into the user's own like public key, and then only they can decrypt that result. It's a really interesting system. There's a big white paper out there for you to read through if you're really interested in like learning more about that. But then once the KMS has performed that key switch, then the relayer can return the result to user 2, they can inspect their balance, and they can see that the transaction has gone ahead. And this is kind of how we understand this at the architectural level. So Zama has very kindly worked with us to actually help us with the implementation of our own testnet, and that has involved understanding a lot about how this is deployed, what the functional components are. So at like the fhEVM level, all you really have is like your L2 nodes, your load balancers, your proxies, etc. Everything that you would kind of use to set up like a standard blockchain. And then on top of that, on the actual gateway component, this is where all the hardcore compute is stored. So you've got your FHE co-processors, you've got your co-processor DB, you've got your relayers, you've got your gateway chain nodes, and then you also have like the KMS enclave type environment, which I believe is based on AWS Nitro at the moment. Now, I know that's subject to change, so all of this should be considered to be somewhat in flux, obviously, with regards to Zama's roadmap, but this is kind of what we've seen ourselves over the course of working with this technology. Okay, there we go. Zama hat off. So our testnet is built kind of out the same components as the Zama testnet itself, but there are some slight differences. So we built our testnet as a standalone L1 rather than an L2, and we use a centralized KMS rather than an MPC KMS. So why did we make these changes? Because that's not really representative of how we see FHE in the blockchain working. Well, our testnet is explicitly for the integration and testing of actual FHE accelerators, which are obviously not something you can pick up on AWS at the moment. Obviously, L4, but we also want to understand the blockchain technical environment from the bottom up. So that means you actually have to get your hands dirty. You actually have to start building something, and that is exactly what we did. And we also just think that FHE blockchains are super cool, and we wanted our own chain to experiment with. Because in the context of FHE, like if you're looking down the barrel of an FHE future, then is FHE going to work in the Web 2 way, where you're connecting your data sources together, or is it going to work in the Web 3 way? And we think that FHE natively is closer to the ideas of Web 3, where the access to data is much faster, And we see FHE going forwards as being something where blockchain will be a significant part of its ongoing technical development for some time. So this is also kind of how we see things as well. So it's really, really hard if you're building really new hardware to be able to get users onto that. Because again, it's not like software. It's not like you can spin this stuff up as an instance on AWS. You have, in some cases, especially for the photonics, an extremely new type of computing environment. And you need to be able to connect the developers who are going to use that to that hardware. And in the FHE space, usable solutions that like a lot of people can pick up and use, those are really, really thin on the ground. Whereas Zama, they're this little spark of divinity here that connects developers straight to hardware through tools like fhEVM. And that is super, super important to us. So thank you again, Zama. Yeah. So this is kind of the architecture of what we've built out at Optalysys. Obviously, it's an L1. And here we're looking more at how you would deploy like a smart contract onto that testnet. So how would you, as a developer, actually gain access to this resource? So you would request ETH from our test faucet. So not real ETH, unfortunately, it's monopoly money for using on our testnet. But you can request that. We will fund that wallet for you. Then you'd be able to use that ETH to deploy test contracts that you're writing using fhEVM. You're writing that in Solidity or something similar. That would be deployed via the JSON URL. Then you can actually test your contract. And just as it happens in like the Zama model that we anticipate, you will be emitting compute events. These will be picked up by our LightLocker systems, and they will process those and they will return the result back to the L1 chain. And then you can examine the outcome of that. You can make sure that the ciphertexts are correctly formed, that the compute was done correctly, and so on and so forth. Obviously, there's a centralized KMS here because we didn't really want to mess with AWS Nitro. But this is kind of like a stand-in for what the key management system that Zama provides. So, yeah, and this is just to sort of kind of emphasize how much of this is built on top of what Zama have done. So there's a number of different architectural components in this. So you have things like the centralized KMS, you have the KMS connector, you have the KMS core, the public storage, etc. You've got your relayer, you've got all the things that go into the coprocessor. So in addition to your ciphertext, you also have like a ZK that proves that you own that ciphertext. This is also like a key component of the coprocessor infrastructure. And all of this stuff is built out of the components that Zama has containerized. We have it hosted via managed Kubernetes on GCP. But we also have physical LightLocker systems that actually listen on the TFHE worker. We listen for those emitted compute events, and we actually run the actual computations on those physical devices, which is kind of what we would expect in a number of different contexts, be that on premises, be that through co-location, be that through as part of like the actual core Zama infrastructure. So why did we build a dApp on this? So anybody out there who currently has one of our pre-funded wallets for working with that dApp, if you're having any kind of challenge with that, if you're having any kind of trouble with that, do like put your hand up. I have some colleagues here, like Aditi here, who will be able to help you connect your wallet to that network and be able to like interact with this D application. But what we wanted to accomplish with this dApp was we wanted to connect developers directly to bespoke FHE systems. However, we do also love to eat our own dog food, so naturally we also wanted to build things on top of it. And what we wanted to do was we wanted to build something that leverages the very specific advantages of FHE in the blockchain. And that basically means shared computational state with logic running over hidden data. We wanted to build it quickly, so we held an internal hackathon and built this in 2 weeks just before we got here. And we wanted to do so openly, so all of the code involved in this dApp is going to be available on our public GitHub. So like I say, we wanted an application that highlighted the specific advantages of FHE. So loosely, this translates to application where some of the data needs to be committed ahead of time, yet remain hidden on chain, where logic needs to be run over that hidden data, and where you have multiple participants interacting with the same data. So the dApp that we built is something that leverages these principles. We commit some conditions that govern like a win or a lose state ahead of time. These have to remain hidden from players, but they should exist before players start to interact with the system. So it's not like we get to the end and then we roll a dice to work out if you've won. We commit the state before we actually allow you to interact. So the dApp we built is called the Doors of Mystery, or Las Puertas del Misterio. You'll be able to find all of that smart contract code on our GitHub. All the logic is implemented in fhEVM. It's implemented in Solidity. So in this game, players must pick which doors have a point behind them. Once the player has submitted all 5 of their guesses, they can then submit them to the contract. And on conclusion of the game, we'll show a leaderboard for the most points scored. We also kind of wanted something thematic, so we based all of the illustrations here on door styles that can be found around Buenos Aires as well. And this is deployed on what we call testnet blue. So we have a dev testnet, which is based purely on CPU. And then testnet blue is actually based on our physical LightLocker systems back in the UK. So for the game we're playing, you'll be running that over testnet blue. On conclusion of the game, a physical LightLocker system will actually be picking up that compute and running that. So if you submit something to this game, it will actually be running on accelerated hardware as well. So we'll get on to actually coming to the conclusion of that game. I mean, I said we handed out some pre-funded wallets. So if you're connected to that, if you've submitted your guesses, then fantastic, thank you. If you want to participate based on what we've just described, there's still time. We do have some pre-funded wallets left for you to use. So if you want to put your hand up, if anybody wants to join at a late stage, we're happy to give you a bit of time just to get involved, maybe wait a little bit before we conclude that game. But what did we learn as well? So we've been working with the Zama sort of like fhEVM environment since January, when we started to have some of our very first accelerators in a very sort of alpha state. So we started working with fhEVM way back at the start of the year, since release 0.73. And 0.73 was very good, but we did have some challenges with it. So in particular, debugging info was slightly more difficult to pass. Examples as well, like the FHE counter, they were useful, but like for building more complicated applications, it was still something that required quite a lot of expert knowledge to be able to work with this. Since we started working with Zama to build this out, of course, we've had a lot of interaction, and release 0.8, the major release, was extremely helpful for quality of life for a dev. So this included things like the Relayer SDK, which made things much simpler to integrate. Decryption took a step up as well in terms of speed. And perhaps most importantly, the working front-end repo with a front-end example for integration, that made things much, much easier to springboard off. So Hard Hat also wouldn't support custom networks, so we did have to write some custom command line interfaces to create like an fhEVM instance with our public contract address, relayer, GRCP addresses, etc. Thank you very much for listening to the presentation of both myself and Nick. We are still available for questions, so if you have any questions for me, like for the room, obviously, like you can relay them to me right now. If you have any questions just for us in general and want to find us after this presentation, we will also be here for a while longer. So thank you very much on behalf of Optalysys. Thank you very much to Zama for inviting us. It's been a pleasure to be here. It's been a pleasure to be in Buenos Aires. And thank you very much to the cafe.